All right. I think we're good now. That's weird. Really weird. All right, thanks for letting me know. Okay. X is less than -3. Notice how we have a hole there, right? So the point actually doesn't exist at -3, so we do not need that bar. Okay. What about the domain piece for our parabola? Lowest x value, highest x value. Where does it begin and end? Good, Dan?
It would be greater than -3, but less than or equal to 2.
All right, so our x's have to be, we have kind of two things going on here. Greater than -3. Notice how the larger side of that inequality points to the x. Okay, so x is greater than -3, but x also has to be less than 2. We can equal 2, correct, on the parabola? So this guy needs a little bar underneath it. And what about the constraint or domain for the last linear piece? Good, Braden?
X is greater than 2.
X is greater than 2. Perfect. So now that we have the equations, little pieces of this graph, we're going to use the equations, because we were talking about that yesterday, to help us evaluate some of these limits. Now, since we have the graph, we can kind of check our work, but let's get started. We're going to get used to starting using these equations in terms of limits. So, if we were to approach 2 from the right-hand side of this piecewise equation, which piece do you think we're going to directly substitute in 2? We discussed that yesterday, how direct substitution is an algebraic way for us to find a limit. Which piece would we plug it in? Anastasia? The one, why? Good, the parabola one? That's the only one that does. All right, so if you're plugging in 2, that means you're equaling 2 between the constraints, so you have to figure out which one would that fall under. And this is the only one that works, because that's the only one that equals 2. So in terms of this limit, we're going to directly substitute in 2 into the parabola equation that we found. Let's see, 2 plus 1 is 3, 3 squared is 9, 9 minus 6, we got 3. So algebraically speaking, yeah.
So even though it's coming from the right, it's still the parabola?
Oh, crap. Yeah, good catch. Okay, if this plus wasn't there, I got ahead of myself. We're going to, Anastasia, we're going to check out that number 2, or part B. No, you were right. Okay. Thank you, Allison. All right, so this plus 2, or that little positive sign means something. Good catch, okay? We want to come in from the right of 2. I got a little ahead of myself, I apologize. Which constraint fits that idea? Numbers that are to the right of 2. Good, Braden.
Last one.
The last one. Okay, my apologies. To the right of 2. So we're going to use the linear function and plug in 2. Let's see, we got -1 minus 1, which would be -2. All right, that's going to make more sense graphically. So notice how we solved it algebraically. Okay, we use the equations and that direct substitution idea. But if we check it on the graph and find that x location of 2, trace the right-hand side, notice how we are approaching a height of -2, like we said the limit would be. Okay? Now on to part B. Let's check this out. If we were to approach 2, do you notice how this one does not have a plus or minus? Okay, so if it doesn't have a plus or minus, that means we have to check both sides. Okay, what's happening from the right, what's happening from the left. Now we already know what's happening on the right-hand side of 2. Okay, pretend we don't have that graph there. Okay, we're just looking off the equations. We already know what's happening to the right. Let's go ahead and we're going to check the left. Which of the 3 equations involves numbers to the left of 2? Close values to the left of 2. Can you tell based off the domains? some close numbers to the left of 2 are 1.5, 1. Okay, which values or which constraints would those numbers fall in? Are we thinking the second? We just don't want to say it? Okay, so let's go ahead and we're going to directly substitute in 2 into the second equation. I think before we said this was 3. Okay, so notice how we said the right-handed limit was -2, the left-handed limit was +3. Does the limit at 2 exist? Does it not exist? What's going on? Braden, shake your head no. Good. Okay, as you come in from the right, you're approaching -2. As from the left, you're approaching 3. Those would not meet up. Okay, so this limit does not exist because the left and right limits are different. Okay, if a limit doesn't exist, it's state why. And we can check that graphically. Okay, at 2, if you were to come in from the right, if you were to come in from the left, notice how they don't match. Okay, let's check out C. If we were to approach -3 from the left, okay, so which one of these constraints involves numbers to the left of -3? The first one. All right, so in our first equation, we're going to directly substitute in -3. Looks like we get 3 minus 5, which is -2. We could check that graphically because we have a picture at that value of -3. Come in from the left, you're approaching -2. Checks out. What if we wanted to approach -3 from the right? Of your 3 equations, which one has those values? Numbers on the right-hand side of -3. The middle one, the parabola. Okay, so we're going to directly substitute in -3. Looks like we get -2 again. All right, so graphically, there's the -3, approach from the right. Notice how you're getting closer to that -2. All right, check out the next one. As we approach -7, no plus or minus, so we have to come in from both sides. Okay, which equation might that fall under if we're going to approach -7? Good, Braden?
First one.
The first one. Okay, now isn't the first one found on the left and the right of -7? Because this one only goes to -3, right? This is on the left and the right. So we only really need to check this one equation because it's not like we're bouncing between -7 anywhere in our constraints. We're only bouncing between -3 and +2. So 7 minus 5 looks like we get 2. Graphically speaking, -7 somewhere right here, approach from the left, approach from the right, looks like we have that height of 2. And our last one, -1, which equation are we going to use? We have to come in from the left and the right, but this one is kind of similar to the -7 one we just did. Where would -1 fall? Go, Braden?
The middle one.
The middle one, the parabola. -1 is within this constraint. So let's go ahead and plug it in. Looks like we'll get -6. Graphically speaking, -1, if we come in from the left and the right, notice how we have that height of -6. Okay? So in terms of piecewise functions, even if you don't have the graph, okay, you have to strategically pick which piece you would be using for that particular limit, okay, based off of the constraint or the domain. We doing okay? Right. Let's try another one. This time we don't have a graph. Consider the function, if a limit doesn't exist, explain why. Okay, so the first one, we're going to approach -2 just from the left. So based off of our piecewise function here, we have to determine which equation falls on the left-hand side of -2. Can we pick it? This one's a little better because we only have two pieces instead of 3. Right, the top, okay? Numbers that are less than -2. So let's go ahead and plug in that -2 value. Let's see, this would be 2 times 4, which is 8, minus 6. And we get 2. So we don't have a picture to check it, okay? But if we were to envision this in our heads, as you approach -2 from the left, your graph is getting closer to that height of 2. What if we wanted to approach -2 from the right? Which piece would we choose? Good, Dan?
You would choose the -1/2 because things greater than -2 are from the right.
All right, so we're going to choose the second equation. Let's go ahead and plug in -2. 1 plus 1 is 2. All right, so what about kind of the overall limit at -2? If you were to come in from the left and the right, would your fingers match up?
Yes.
Yeah, you can tell that based off of the evaluation we did here. As we come in from the left and the right, they're meeting up at a height of 2, so this would be 2. We don't have a picture to check it, but at least the calculus is working out. Okay? All right, let's try some more. These aren't necessarily piecewise functions, but this is just more practice with the direct substitution that we discussed yesterday. We're gonna look at some more or some different types of functions like natural logs, maybe some trig functions in there. But the first step should always be direct substitution, just to see if it works out. Okay, so let's go ahead. In this case, we're going to substitute in that letter E. E is actually a number. Do you remember what that number is? Like pi is 3.14. Do we know what E is, roughly? 2.718, yeah. Okay, so I'm curious, the natural log of E, without a calculator, do we know what that is? Simplifies to? Go, Dan?
1.
It is 1. Okay, so there are 3 natural log evaluations that we have to be very, very familiar with. Those are the natural log of E, the natural log of 0, and the natural log of 1. They're all very similar, which can make them confusing, but these are the easiest ones to solve without a calculator. The natural log of E, we said, was 1. What about the natural log of 0 or the natural log of 1? It's a little tricky. Okay, the natural log of 1 is 0, and the natural log of 0 is undefined. Okay, those are 3 natural logs we have to become familiar with. So in terms of this limit, after we use direct substitution, looks like we get 1 over 2e. Now we can't simplify that any further. I know it looks weird, but again, this is representing a height on your graph. If you were to approach this 2.718 value on the x-axis, this is the height that your graph would be approaching from both sides. Okay? Let's go ahead and check out the next one. We want to approach 5 from the left. Now, in terms of direct substitution, we're just going to plug in 5 and see what happens. Let's see, 5 squared is 25, 25 times 2 is 50. And then 50 divided by 5, we got 10. Plus another 10 would give us 20. We doing okay? Direct substitution from yesterday? Let's check out the next one. Sine squared, we're going to plug in pi. Alright, without a unit circle, because this is one of the points that we have to know. If you were to go to the pi location, what would the sine value be of that ordered pair? Good? 0, yep. Alright, now this was sine squared, so we would eventually have to figure out 0 squared. And then at that same location of pi, what would the cosine value be? Yeah.
1, which times 2 would be 2.
This is actually -1, because you're on the left-hand side.
That's right.
Yep, you're on the left-hand side. Okay, so 0...
Oh, I put that down.
Okay. 0 squared plus 2 times -1 looks like we get -2. Alright, time for some trickier trig. We're going to plug in 5 pi over 3. This is not one of the easy ones you have to know, so I'll let you check it. Okay? So on the unit circle, go to 5 pi over 3, find that ordered pair, and we want the tangent value, which means we have to do some division. I forget what page your unit circle's on. 10? Okay. Can we find it, Dan? Go ahead.
Yes. The tangent,
Yep.
5 pi over 3, would be, which is sine over cosine.
Correct.
Cosine.
Yep, sine over
So
cosine.
Sine, which is negative square root of 3 over 2,
Yep.
is over the sine value of 1/2.
Perfect.
Which, in order to divide by fractions, you would multiply it by a reciprocal,
Yep.
giving you a total number of negative.
Alright, so to figure out the tangent, we need the sine value divided by the cosine. Instead of dividing by a fraction, you could multiply by the reciprocal. The 2's would eventually cancel each other out, and you're left with a negative square root of 3 over 1, which is just a negative square root of 3. Alright, now in the bottom, we have to square 5 pi over 3, so we have to square both the top of that fraction and the bottom. If we square 5, we'll get 25. If we square pi, we get pi over 2. And if we square 3, we get 9. We're doing okay? So right now, we essentially have negative square root of 3 over this fraction. We might have to do a little bit more. So instead of dividing by a fraction, let's multiply by the reciprocal. And it doesn't really look like anything's going to cancel out or simplify for us. So we can just say negative 9 square roots of 3 over 25 pi squared. Very weird answer, but again, it's representing a height. Okay? Let's check out our next one. Direct substitution, plug in negative 2. What do we get? 0 over 0. Do we remember what that's called There was like a term we used yesterday, yeah.
The indeterminate form.
Indeterminate form, okay, 0 over 0, indeterminate form. And do we know graphically what's happening at this -2 location on the x-axis? There's a hole, okay? So, if you think about a limit in terms of a hole, as you come in from the left and the right, it's going to match up, meaning the limit does exist. It's just that at -2, you have a hole. So we have a little bit more to do here to help us figure out what that limit value is. What might you want to try? Can we, factoring, let's try factoring. All right, so factor the top. Two numbers that multiply to -6, add to -1. Can we think of those? Okay, +2. Can we factor the denominator at all? Maybe not using that same technique, but there is a different type of factoring, yeah.
We can take the 2 out and get an x plus 2.
There we go. We can use a GCF. We can take out the greatest common factor, which is a 2. Now that it's factored, notice how the x plus 2's would cancel, right? So our simplified form is x minus 3 over 2. So even though the direct substitution of -2 didn't work at the beginning, okay, because we found out we had the hole, let's go ahead and try it now that we have this simplified form. So if we plug in -2, looks like we'll get -5 over 2. And since this is a height, okay, that's the y value or the height of your hole. As you come in from the left and the right, this is the height you're approaching. We hang it in there? I know it's hot. Okay. Let's go ahead and try some more. All right, these are all equations, no graphs or tables. We're using just algebra in this case. Let's try direct substitution. Plug in 3. What do we get? 8 over 0. All right, so we can't divide by 0. This really isn't giving us an answer, but do we know what's happening graphically? Go, Stevie? There's an asymptote. Okay, so in terms of a limit, we know there's an asymptote at 3. If you were to come in from the left side of an asymptote and the right side of an asymptote, would those two sides match up? No, because in an asymptote, they drastically curve, right? Either both drastically up, both drastically down, or in opposite directions, right? But they're never reaching the same height, okay? So this is an automatic does not exist. Whenever you have an asymptote, the limit does not exist. All right, let's go ahead and try the next one. A little tricky because we're plugging in a fraction. Okay, we have 3/2, but go ahead and give it a shot. Any takers when you plug it in? 0 over 0. What's happening graphically? We got a hole. Okay, so the limit does exist. Okay, we just have to do a little bit more figuring out. What do you want to try? You want to try to factor like we did in the last hole example? This one's a little tricky though because you see how this is an x cubed. Okay, we're going to review how to factor cubics for a second, okay? You don't have to write this down if you don't want to. These are very uncommon, but it's still something that I want to go over. So what we're dealing with in this case is, I'll write this down, we have 8x to the third minus 27. So that's going to fit this format. See how we're subtracting? Okay, sometimes you could be adding, but we fit this one. So we need to figure out what is the perfect cube of the first term and what's the perfect cube of the second. Can you think about what number times itself 3 times would give you 8? 2, okay, and then what variable times itself 3 times would give you x cubed? That'd be x, right? What number times itself 3 times would give you 27? Not 9. 9 times 9 times 9 would be really huge. This would be 3, okay? So this is considered kind of the a value and the b value in this setup. So in order to factor 8x to the third minus 27, we would need 2x minus 3. And then the other factor pair, we would have 4x squared. Okay, we're squaring this 2x. We would then have a 6x. Okay, 2x times 3. And then lastly, we would have 9, 3 squared. If this was 8x cubed plus 27, we would have used kind of this method. Notice how the first factor, the symbol matches the operation in the original expression. The first symbol in the second group is opposite of what you start with, and the last operation is always a plus. Okay, the A, B, and C, or the A's and B's don't change. It's just the symbols. So in order to factor 8x cubed minus 27, we're going to go ahead and write this down in our notes. Okay, we have 2x minus 3, and then 4x squared plus 6x plus 9. So that's how the top factors. We can't really factor the denominator. What's going to happen? Go, Stevie?
Top and bottom cancel out.
Top and bottom cancel. All right, so all we're left with is the numerator, and we want to go ahead and substitute in that 3 halves. We're going to try it again. Even though it didn't work initially, we're going to keep trying it until it does. Okay, so let's see. If we square 3 halves, that would be 9 over 4. Times 4 would cancel out the 4, so we're left with 9. 6 times 3 halves would be 18 over 2, but that's 9 again. And we have the plus 9 on the end. So it looks like our limit, our height of the whole, is 27. Okay, a little tricky factoring, again, not very common, but in case you do see it, I just wanted to pop that up. All right. What about our next one? Can we try direct substitution? Plug in -2. What'd you get? Do we get 0 over 0 again? Okay. Are you starting to see a pattern with these? Okay, they're probably not always going to work out nicely, so you're going to have to do some extra work. All right, now we ended class yesterday with this example. Whenever you're dealing with a square root, we have to use a particular method to get around that. What are we going to do? Maybe reference yesterday to help you out? What do you want to try? Square roots are tricky. Because so far, the only technique we've seen to get around a whole is to factor, right? But we can't factor anything here, so we have to use a different technique. We're going to use a conjugate, right? Okay? So how do we find the conjugate of this square root numerator? How does a conjugate operate?
Isn't it the opposite?
It's the opposite what?
Numerator? The second symbol?
The symbol, right, the operation. So that's going to change to a +1. We're going to multiply that in the denominator as well. Because it's a fraction, you got to keep it balanced. Alright, so we're going to actually go through and multiply some of these together. We're going to multiply through the conjugates, which in this case is the numerator. But in the denominator, they're not conjugates. So I don't really want to go through and do that multiplication. We're just going to keep them as the separate factors. But let's see what happens in the top. Okay, if we go through that FOIL distribution process, I think we said yesterday, didn't we, that the insides and outs, or the outsides and insides would always cancel each other out because one's positive, one's negative. So all we have to do is take the first terms multiplied together, which would just be 2x plus 5. The square roots would cancel each other out. And we only have to do the last terms, which would be -1 times +1, which would be a -1. So let's go ahead and clean it up. 2x plus 4 over that denominator. You see anything else we could do? Yeah? Maybe? What do you think, Braden?
After the top.
Let's go ahead. Now, we eventually want something to cancel out. Okay, that way we can get a simplified version. So we haven't canceled out anything yet. That means we could probably do something else. Let's go ahead and factor the top. We can pull out a 2. And by pulling out that 2, notice how we can now cancel out the factors of x plus 2. Okay, so our simplified form is 2 over that square root of 2x plus 5 plus 1. Let's now go ahead and try direct substitution again. It didn't work initially because we got a hole, but we're going to try it again to figure out the height of that hole. Let's see, if we plug in -2, this would be -4 plus 5, which is 1. Square root of 1 is 1. Plus 1 is 2. So it looks like the height of our hole is 1. We doing okay? Can you guys try the last one at the bottom? Always try direct substitution first. Okay, if it doesn't work, you may have to use some type of technique to simplify your equation. Alright, you may not be done yet, but that's okay. Can we all get to at least the point on the board right here? After you multiply things through? Do you have any questions on the work up to that point? Okay. We still haven't canceled anything out yet, so there's a little bit more we have to do. Do you notice anything we can try? Good, Dan?
You can take the -2 out of the top and
Okay.
use it as a GCF to factor it downwards.
There we go. Okay, so take out a -2. We still haven't canceled anything out yet. So again, there's a little bit more we should be able to do. You want to keep going? Okay.
The x squared minus 1 is a perfect square, so
Okay.
therefore you can factor that even more to get x minus 1 times x plus 1.
Okay, so difference of perfect squares up top. And what's going to happen?
The x minus 1 is going to cancel out.
X minus 1 finally cancels. Alright, so now that we simplified it, okay, we removed something from the problem, aka that hole in our graph. Okay, it's not there. Try substitution again. Go ahead and plug in 1 with what's left up top and what's left down below. So even though there's a hole at 1, as we come in from the left and the right, what is the height of that hole? Can we find it? Good, Dan? Did you get it? -2. Can we get that when we plug in 1? Yeah? Perfect. Have a great weekend. We'll do a little bit more on Tuesday. Summer assignment, guys, Tuesday. Let's not forget that. Summer assignment Tuesday.
You're not getting